Hey folks. All right. Well, now that we've looked at context-free grammars, we want to get into the context-sensitive side of things. Again, the context-free grammars could only look at the structure of a component and say, okay, well, this looks like an if statement, but it has no knowledge of what happened before the if statement or what's going to be, after the end of the if statement. So it's just got the structure of that one individual component. So now we want to augment that and say, well, if the if statement says something like if x is less than y, then I need to be able to check that x and y have actually been declared. I need to check that x and the less than and y are all of compatible types, and I have to make sure they're in the right scopes. All of that sort of thing has to take place somehow. So we want to come up with some means of augmenting our context-free structure for describing a language with this extra context-sensitive information. So that's where we'll go today. So we want to make sure, again, things like check that variables and functions have been declared before we try and use them. Checking that the different data types are compatible, right? That all of the operands and the operation are of compatible types. We need to go through and insert implicit type conversions where they're necessary. We need to go through and figure out how and when different things' values should be updated and computed. So we need extra functionality on top of the context-free grammar structure that we built. Now, again, what we're going to wind up looking at are things like Lex and Yacc and other tools that allow us to provide a formal language description of, or a formal grammar describing a language, and then the tool, Lex or Yacc, or the combination of them, will go through and say, okay, well, now that you've given me the grammar, I will build a program that can go through and tokenize source code in that language, or go through and build a tool that can compile programs written in that language. So that does mean that we need ways to kind of describe how our augmented grammars are going to work. So again, context-free grammars apply their rules without any knowledge of the context that they exist in, right? What happened before or what will happen after. So it can't do things like type checking or check for declare before use. So our augmentations have to provide some way of communicating extra information beyond just the syntactic structure. So as a derivation goes on, they can say, okay, figure out what the right derivation is, and then add all this extra information in with the pieces of that derivation. So if the derivation says that this statement is an assignment statement and figures out that that's a variable, an assignment operator, and then an integer or something like that, to make sure that our augmentations can go through and say, okay, well, associate, figure out the scope of the variable, figure out the type of the variable, figure out what specific assignment operator we're looking at, figure out the value of the integer, figure out the value of the expression on the right-hand side, make sure they're compatible, that kind of thing. So all that information has to be somehow associated with the components that we identified in the derivation. So we can either associate extra data with the step or with the components in it, or we can have separate tables someplace that are keeping track of information so that we can look up the data when we need it. So let's say we've got a simple expression, just x times y. All right, so this is buried somewhere deep within whatever else is going on in the program. So we've got this expression, and we need to know what the data type is for each, and we need to know that each of them has been declared. And we need to know if there are, what scopes they're in, if there are multiple different x's in different scopes, which one is this referring to, for instance? If this is the local variable x or the global variable x. All right, so our derivation is going through and figuring out, okay, well, I've got this multiplication expression, it's got the mult symbol, it's an asterisk, it's got a multiplication expression on the left-hand side, again, based on whatever the grammar rules for the language are. That's some kind of a simple type, that's an identifier, and that's specifically the identifier x. And then over on the right-hand side, we've got some kind of a simple value, and that's actually an identifier, and that's actually the identifier y. So what's going to happen is it's going through and figuring out, okay, I've got a multiplication expression right now, or maybe I've got an expression. It looks like a multiplication expression. It looks like the pieces are this. right? So it's going through and doing the derivation top down, figuring out what kind of structure matches what I've got. And once I've gone through and identified the structure, then I can say, okay, well, I've got an identifier x. Maybe it's an int. So I can say, okay, I've got an int on this side. I've got an int on this side. I've got an int on this side. And over here, maybe y is a float, for instance, and say, okay, well, now that I've figured out it's y, I look it up in my table or whatever and figure out, okay, y is a float. It's a float. So at this point now, I can figure out that I've got an int multiplied by a float. So you get this top-down process where you figure out what makes up your multiplication expression, and then this bottom-up process where you're saying, okay, now that I know what it's made up of, I've got more information. I know that the thing over here is an int. I know that the thing over here is a float. And so I know I've got an int times a float, which gives me extra information about what has to happen in that multiplication operation. Maybe there has to be an implicit cast of this thing on the left-hand side to float, right? But we get this two-part process of a top-down derivation and then a bottom-up evaluation, so to speak. And so that's what we're discussing here, is our parse trees, are generally produced recursively. Well, actually, we'll get into alternatives to that in the compiler course, but our parse trees are generated from a sort of top-down approach where we start with this generic start non-terminal, and down at the very bottom of this giant tree, this derivation tree, we've got the tokens that are the actual source code tokens for that particular program. And again, as we're doing this sort of top-down approach where we're figuring out, okay, well, I've got my program is a set of statements. And then I say, okay, well, it's a statement followed by more statements. And then that set of more statements is a single statement. And then I go through and say, okay, well, that first statement is an assignment statement. That second statement is a print statement. Right? We can go through and build our derivation tree, our parse tree for the program top down. And then once I know what the pieces are, I can evaluate them bottom up to say, okay, now I know that that first statement is an assignment statement. It's got this variable is assigned this value. And I know my print statement is a print of this variable name and this other value, or this string literal or something. So we go through this top-down parsing, this top-down derivation, and then a bottom-up analysis once we've got more information about the pieces. Now, there's a couple of different ways that we can attack the problem of trying to get context-sensitive information distributed and updated. It's fairly common to use a lookup table someplace where you say, okay, well, as I'm going through and analyzing each of the statements in a program, for instance, if I see a declaration statement, I'll say, I've seen a declaration for a variable named X, or I've seen a declaration for a variable named Y. And so you start adding information about these to the table, where you say, okay, I saw an X, it's in this scope, it's got this data type, and it's been initialized with this value. And then as you see later statements, as you're going through and you see a statement like, y is assigned x times 3, you can look up and see if y has been declared, and if so, what data type it has. You can look up and see if x has been declared, and if so, what data type it has. And so you can go through and start using these symbol tables to make sure that the semantic rules of the language are being followed. Right? So this is using the information from your symbol table above and beyond just the basic structure of the program. So you can go through and keep track of all sorts of different information. Again, you can do similar things with keeping track of scope, right? Which identifiers are in which scopes. You can go through and have maybe a table that keeps track of defined functions, all sorts of different things that you can keep track of using a similar approach. An alternative, and this is kind of a Lispy approach to things, is to say, well, instead of having this separate symbol table, what I'll do is I'll actually pass everything I know about the current environment along with each of the different pieces of the parse tree. So when I see, when I decide that I've got an expression, and I'll say, well, associated with this expression, here's a list of everything I know that's been declared. And then that gets passed to the right-hand side of the expression, the left-hand side of the expression, if there's a value operator value type of thing. And then as you're going through and evaluating the left-hand side of the expression, for instance, you'd say, oh, this seems to be made up of a this and a this and a this. And so for each of those, you pass along the environment information to that. And so you wind up passing lists of environmental information more or less as parameters to whatever functions are analyzing or doing your derivation, doing your parsing of the program. So if you can think back to the joys of lambda blocks and that kind of thing in the programming languages course, they actually passed along extra parameters that had sort of 3 environment lists that might be the different environmental information that's relevant to the derivation process. Now, those can get quite large, right? But if you're going through and saying, okay, well, I'm going to pass all of the environment information along to this next part of the derivation, and I'm going to pass all of that along to the next part of the derivation, then I'm going to add something to it and pass that along to the next part of the derivation. If you've got this huge parse tree that's going on, you've got a lot of information that's being passed back and forth. And so this can get kind of large and cumbersome from a data volume point of view, but it also means that each individual piece of the derivation has its own unique little view of its own environment that's kind of independent of everybody else's views of their environment. And you don't have this global table that's keeping track of everything for everybody. So it's a very different approach, but perfectly valid. So what we're going to be doing in a practical sense is working with Lex and Yacc to take care of, for Lex, the regular expression side of things, and for Yacc, the context-free grammar and augmented grammar side of things. And so these will go through and allow us to associate tokens and or associate data with our tokens and with our components, our non-terminals in a derivation. So that can contain all sorts of interesting information about, for instance, the scope that the token was declared in, the type of the token, extra data. So for instance, if the token represents a string literal, then you might have extra data associated with it that says, okay, well, here's the actual text for the string literal. Here's here's whether it's a constant or a mutable or non-mutable token. Here's extra information that's associated with it. If it's a variable, what scope was it defined in? What data type does it have? What current value is associated with it, if any? So all sorts of extra information we can associate with the components in our derivation. This is also going to allow us to create essentially things like symbol tables if we want to, or global variables that we can use to keep track of information during the derivation process to allow us to support that augmented information. It's going to allow us to create C functions that we can run during the derivation process to determine, to do something like, if I see a variable declared, I can look up whether it exists in the symbol table. If I see an assignment statement, I can look up to make sure that the data types on both sides are actually compatible. Or to go through and say, okay, well, this one's a float and this one's an int. I have to do this to convert the int to a float value before I apply the operation. So we can start going through and adding lots of semantic information and C code to support that in our derivation process, or in our compilation process, for instance. So Lex and Yacc will allow us to follow the sort of symbol table approach to augmenting the semantic information in our grammar. But we'll get into the mechanics of that when we look at when we look at Lex and when we look at Yacc. All right, I will leave that there.